Last time we talked about graph algorithms, some basic graph algorithms like DFS, BFS, DSU, stuff like that. This time we'll go over some more advanced graph algorithms and go over a little bit about how to use them, but I don't think we'll have time to talk about any example problems. So anyways, yeah, let's get into it. So here's some more advanced graph algorithms. So these are algorithms that go beyond just a simple DFS, BFS, or DSU. So there are going to be a couple of them today. These algorithms will be used to solve the following two problems: shortest path problems, where you can use various shortest path algorithms. Each one has its own unique like advantages and have their disadvantages. Same with minimum spanning tree algorithms. Some will have advantages in terms of time complexity, others will be easy to code, etc., etc. So here are the basic things. So let's talk about shortest paths. So remember last time we used BFS to solve shortest paths, but that's because in our graph, or let's say in our network of cities, um each road took the same amount of time to travel. So if you wanted to travel to city B, then you would just need to count the number of roads. Let's say that there's a lot of traffic, and so that means that different roads will take different amounts of time to travel. So now we would need to basically assign a weight to each road, which is basically the amount of time that it'll take to traverse that road. So now we call this type of graph a weighted graph. So how would we solve shortest path? Well, there are two algorithms that are common. There's actually three, but I won't go over all three of them. Two of them are Dijkstra's and Floyd Warshall's. So Dijkstra's algorithm is the most standard one, and Floyd Warshall's is a pretty cool trick, but won't be very useful in and of itself. But its idea will be extremely useful for many problems. So yeah. So Dijkstra's algorithm. The idea behind this algorithm is as follows. So you basically start at the root of the graph. And now think of so now if we define the distance of a node as the distance from that node to the start node, or from the start node to that node, then we can think of kind of like a sphere around the root node. Every time we process a vertex within the sphere goes larger based on the cities that you can go to, and you essentially have like a sphere of possible cities that you can go to each time the sphere expands to include more cities. This is kind of the idea, except more formalized. So what we're going to do is we're going to have a priority queue over all of the cities within the list that we still need to process. So for example, in the last time, we used a queue and we said, think of this as like a to-do list, right? So we have a to-do list containing a bunch of different nodes that we are yet to process. And the next node we'll process, we will add its corresponding tasks to the end of the queue. So yeah, so last time we had a to-do list, and essentially we were processing a task at the start and then moving the corresponding tasks that come from that task to the end of the queue, right? This time, we're going to have a priority to each of those elements within the queue. So think of like a to-do list of a bunch of different cities that we want to visit. We haven't visited yet. So now we take the top priority, the thing we want to do very first. Now we remove it from the to-do list. We essentially complete that task. And now once we remove that from the to-do list, we add all of its corresponding tasks with its priority to the new to-do list. So now the new to-do list will give us the most important item, the item we want to process first, and then we'll keep doing that until there's no items left in the to-do list. So this is essentially kind of like similar to the BFS algorithm, except this time we're keeping a to-do list that's more sophisticated in terms of the fact that we have priorities. We want to keep track of which one we want to process the first, and after we process it, we have weights assigned to each of the cities. Yeah, and this is clearly guaranteed to work, and the time complexity of this is O of n log n. And the reason there's a log n here is because when we add to the to-do list and we want to find the highest priority item to get out of the priority list, priority queue, it's actually impossible to do this in less than log n time. So actually, the time complexity would be m log n, where m is the number of edges. But yeah, so we're basically adding to the to-do list. We're finding the smallest element within the to-do list, and then we're getting rid of that element. We're adding all of its corresponding cities that it can go to, and then we repeat. So it's very similar to the BFS, except with a more sophisticated to-do list. Yeah. Floyd Warshall is very, very different. So it's a bit more complicated to prove. I won't go into the details as to why it works every time, but the general idea is as follows. So consider all possible intermediary nodes. So let's say you had a path from, oh yeah, I can't annotate. So let's say you have a path, oh. Okay, so let's say you have a path from I to J, right? And you want to consider essentially all intermediary nodes. So if you've already constructed a partial path from I to K and a partial path from K to J, then we can combine those two partial paths and create a path from I to J. So that's essentially the idea. So we're first we're first iterating through all of the intermediary nodes, and then at each intermediary node we relax essentially based on if the partial paths are better than the path we already have, then we update the path we already have to something to the sum of the partial paths. So for example, in here we say if an intermediary node K has dist ik plus dist kj is less than dist ij, that means that combining the two partial paths is going to be give you a better path than the path from I to j. Then we can relax the distances and make dist ij equal to dist ik plus dist kj. Essentially, we're making the new path from I to j the sum of the partial paths, if the sum of the partial paths is better. This uses an adjacency matrix, which like I didn't exactly explain how to do last time, but it's pretty simple. And although the idea is very niche in terms of the fact that the algorithm itself is rarely ever useful, because if you think about what the algorithm is doing, it's finding all pairs shortest paths, which essentially from any node A to any node B, find the shortest path from A to B. But because if you think about Dijkstra's, right? Dijkstra's finds the shortest path from a node A to every other node. So if you run Dijkstra's n different times, then you would get a time complexity of mn log n. And the thing about this time complexity is that in the worst case, if m, which is the number of edges, is n squared, even then, Dijkstra's isn't much worse than Floyd Warshall's. So when you're directly computing shortest paths, you almost always want to use Dijkstra's. So when would you want to use Floyd Warshall? Well, Floyd Warshall itself isn't very useful, but the idea behind Floyd Warshall is extremely useful. And so essentially, what we want to do is let's say, um, let's say like, so what we want to do is, let's say, there are only some certain nodes that can be intermediary nodes, then you don't really know how to use Dijkstras. Like, it's kind of hard to use Dijkstras on that. But if only some certain nodes can be intermediary nodes, well, that perfectly fits in Floyd Warshall. And that could even speed up Floyd Warshall. Because let's say you have like 1,000 nodes within your whole graph, but only 20 of them can possibly be intermediary nodes based on the constraints of the problem. Then instead of n cubed, it could be n squared times 20. And that's a lot faster, while also it's very hard to do with Dijkstras. So there are a lot of situations like that where Floyd Warshalls can be extremely useful, and Dijkstras is not as potent. So the other problem category that I wanted to talk about was minimum spanning tree. So now let's say you have a network of cities, but this network has too many roads. So because it has too many roads, it has become too costly to maintain. So each road, in order to maintain that road, there's a specific cost, and we want to find the minimum minimum total cost we need to spend in order to keep every city connected. And every city connected means everything within the same component. Not just that it's connected to some other city. Every city must be connected to every other city. So this problem is called the minimum spanning tree because if you think about the roads that you keep, the roads that you keep will form a tree, and that tree quote unquote spans the graph by covering every single vertex. So that's why it's called the minimum spanning tree, because you want to find the minimum cost of a spanning tree. Yeah. So how would we do this? Well, the first well, there are again a few ways to do this. There are 3 algorithms that are very popular or very useful, I guess. I'll only talk about 2 of them here. So the first one is Kruskal's, and the second one is Prim's. So Kruskal's is much easier to implement and understand, but there are many situations where Prim's would be better, so it's important to know both of them. So what is Kruskal's algorithm? Well, the idea is essentially to sort all of the roads in increasing order of cost. And now for each edge, if it connects 2 cities within the same component, you don't do anything because that road would be essentially useless. But if it connects 2 cities with within a different component, then it's the best way to merge those 2 components, and that means that you want to include that road within your minimum spanning tree. So it's pretty easy to see why this works using a greedy argument, and it has a time complexity of m log n, and the reason is because you need to sort all of the roads in increasing order of cost. And if you're curious how we would check if they're in the same component or merge 2 components, this is exactly disjoint set union from the previous lecture. So remember, disjoint set union, we could merge 2 components, and we could check the identifier of a specific component. And so in order to check whether 2 cities are the same, we can just check whether the 2 identifiers are the same, and if they have the same identifier, that means they're in the same component. So that's a pretty neat way to be able to implement Kruskal's algorithm, and it's actually very, very short, especially if you have a DSU template. It's really just sorting, and yeah. Yeah, okay. So now let's talk about Prim's algorithm. This one is a bit more complicated to explain, so let's I guess dive into it. So with Prim's algorithm, instead of building a minimum spanning tree over the roads, like considering which roads we add or basically using the roads to consider which roads we add, let's try to use vertices. Let's try to use cities to determine which roads we add. So how does this work? Well, let's say we choose any arbitrary city. Let's say city 1, the capital city, or whatever, right? The capital city must be connected to at least one other city, right? And so the easiest way to connect it to any other city is to just connect it to the city that has the least cost among all of the cities that the capital city is connected to. So now that we've merged those two, now let's say we just merged them. Now we have like a super city, because we don't care that they're in two different cities, because they essentially function as one city. They're one component, and any edge you take will essentially it'll always work the same if it's just one super city rather than two individual cities that are connected by a road that we've already taken. So let's say we merge those two. Now we have a super city. Now we can do the same thing. From that super city, take the minimum possible edge from that vertex. Merge those two, create a super city. And this is an extremely effective strategy. It's actually pretty easy to visualize why this is provably correct. And also, there are two different implementations that can make it either run in m log n, which is number of edges times log n, or n squared, depending on your implementation. And the way you would make it run in m log n is every time you iterate through, like, for example, if you have first city, right? You've iterated through all of those edges, so now you add all of those edges or all of the nodes that correspond to those edges into some sort of priority queue, like a to-do list. Similar to the to-do list of the Dijkstra's algorithm, you add all of these nodes into a to-do list. You get the best node from the to-do list, and then you add all of the other nodes. It's very, very similar to Dijkstra's, except the difference is like in Dijkstra's, you keep a distance for every single node, and so the distance, the weight of the node is essentially the distance from that from the start node to that node. Except in Prim's algorithm, the weight is just the edge that you have to add in order to keep that node. So yeah. So like now that you have that, another difference between Dijkstra's and Prim's is that, like, with Dijkstra's you're individually calculating distances, but with Prim's, every time you take an edge, you just add that to your answer and then move on. Essentially, you don't care about what the distance to that edge is or whatever. So Prim's is a pretty interesting way to it's a pretty interesting way to compute the minimum spanning tree, in the sense that instead of using roads to figure out which roads, we're using cities to figure out which roads to take. So that's the m log n solution. What about the n squared solution? Well, the n squared solution is pretty much the same thing, except it uses a slightly different implementation. So the different implementation is the fact that instead of using a priority queue, because that'll be log n if there are n squared edges, so that would be n squared log n. Instead of doing a priority queue, what if we just brute force it? Every time, look through n different nodes and see which of the n different nodes is the best. And if we do that, then we'll provably run in O of n squared, and it'll be even easier to implement than the priority queue shenanigans. So as you see, like Prim's algorithm, if you have n squared edges and and you can't do n squared log n, then you really want to use Prim's algorithm, because Prim's algorithm can give you an O of n squared solution, whereas Kruskal's algorithm, like this, can only give you O of m log m solution. So yeah, you should use Prim's algorithm. So in fact, we actually have some time remaining. So let's look at the first problem within the good problems list, and like let's go over like how to do this essentially. Okay, I'll give you guys a couple minutes to read the problem, and then I'll go over how you would approach this problem. Okay, hopefully you were able to read the question in this time. So now I'll go over essentially how you would approach this problem with shortest path algorithms. So the idea behind this problem is that, let's say you know the exact path that each cow would go on if there is no shortcut. Once you know that, you can actually pretty easily determine where you want to put the shortcut trail, because if you just look at a certain node, if you want to put the shortcut trail at a certain node, then you can calculate exactly how much time the shortcut trail will save, because you know exactly how many cows will go through that node and what the distance from that node to the start point is. So we just need to find find the path for each of the cows, and find how many cows will go to each individual node. So the way we would do that is we would try to construct what we call a shortest path tree. And in this shortest path tree, we would essentially construct shortest path the exact same way, except we want to keep track of the parent of the we would essentially run Dijkstra's, except we want to keep track of the parent of each you want to keep track of the parent of each node. So the parent is like the node that goes to it. So when you're going back, when a cow goes from node X back to node 1, the parent is the next thing it'll go to, and then it'll go to the next thing and the next thing and then so on. And so if we're able to construct the parent of each node, then we can construct a tree, the shortest path tree. And once we construct the shortest path tree, we can easily query what the answer is. So how do we find the parent? Well, consider our Dijkstra's, right? Consider our Dijkstra's, right? When we're doing the priority queue, all we need to do is we just need to store an extra parameter, and that parameter is which node you came from. So if you came from node X, then you just add that node X, like you add X as a parameter to all of the things that X can go to, and whenever you take an element that X goes to and it has a tag node X, then you know that X is the parent of that node. So once you do that, this problem becomes really easy. Um, so the little bit of tricky part is the lexicographically smallest. And the way you deal with lexicographically smallest is when your priority queue is sorting, right? You first sort it by its weight, and then after that, you sort it by its index and or index of the tag. And what that does is it allows you to essentially automatically lexicographically sort or find the lexicographically smallest path. And that'll always, and the reason it'll always find the lexicographically smallest path is because every time you're going to the lexicographically smallest node, and so um, and also like whenever you set the distance, it's always going from the node with the smallest lexicographic number. So if you just keep the extra tag and sort by the index secondarily, then you will always be able to get the shortest path tree in lexicographic order, and then you would be able to pretty easily solve